Today we're going to look at mineral properties. We're going to try to determine how does someone go about identifying a mineral. We will need to be able to identify all of these minerals. Notice olivine is green, pyroxene, this one here happens to have a nice sheen to it. We've got amphibole, our micas here, biotite and muscovite. We have our feldspars here in the middle. We have halite or table salt, gypsum, limonite, hematite, calcite, and quartz. These are some common minerals. So how are we going to go about identifying them though? First, we're going to need to go through a process of observation and testing. Each mineral has unique characteristics that we can determine. After we've gone through some simple tests, we can more confidently identify what the mineral is by name. So there are different descriptions and characteristics that define a mineral. Suppose you bought a new shirt and you tried to describe it to somebody over the phone where they couldn't see it. You might describe its color, the fabric, the way it feels, the length of the sleeves, the way it fits, etc. Minerals have characteristics and properties that are used to identify them also. You might think that color is a good way to determine a mineral, but if you look below, all of the samples below are different forms of quartz, that the slightest amount of an impurity, an element other than silicon and oxygen, or SiO2, changes the color of the mineral. Also, many colors have the same color, or many minerals have the same color. So the different properties of minerals that we're going to look at. We'll look at crystal form or crystal habit, the color, streak, luster, hardness, cleavage or fracture, and on an upcoming lecture I'll give you special properties of minerals, including these topics here. So we're going to start looking at minerals, we're going to start testing minerals, and we're going to try to determine some unknowns in class. So crystal form, or sometimes called crystal habit. Here's an example of halite. The mineral we call table salt has a cubic crystal habit. In this case, it has this very nice, perfectly three-dimensional planes that are of equal sizes. In this here, this would be a perfect crystal form, which would be euhedral, would be cubic. So crystal habit. In mineralogy, crystal habit is the characteristic external shape of an individual crystal or group of crystals. A single crystal habit is a description of its general shape and its crystallographic form. When a mineral has enough space to grow, it can grow into perfect euhedral crystal form. Under most conditions, though, minerals do not take on their perfect crystal habit. As a mineral crystallizes in its environment, it grows into the space available. Minerals generally do not have ideal or perfect growing conditions when they're forming or when they're crystallizing. As a result, most minerals do not display their perfect crystal habit. Many rocks composed of minerals have intergrown crystals that do not display the perfect crystal form. Mineral color. Colors can be deceiving. Color is the first thing someone notices when viewing a mineral. Color is also one of the big reasons that attract people to minerals. But generally speaking, color is not a good property to be used in identifying a mineral. It's usually the first property to confuse a novice collector into making an incorrect identification. Many minerals have different colors, and different mineral colors are used then to identify other minerals' colors. So color in minerals is caused by the absorption or lack of absorption of various wavelengths of light. It's really kind of a light and optics topic. The color of light is determined by its wavelength. When pure white light containing all wavelengths of visible light, right, the Roy G. Biv, enters a crystal, some of the wavelengths might be absorbed, while other wavelengths may be emitted. If this happens, then the light that leaves the crystal will no longer be white, but will have some color. As stated on a prior slide, all the minerals pictured below are quartz. The slightest impurity influences the color of the quartz itself. So they can be different colors while they're all quartz. So color is not that good. An optical quality of a mineral includes how light interacts with the mineral's surface. So here we see a transparent surface. Light is able to be transmitted through the mineral with specific details clearly observed. Translucent is saying, well, some light is able to be transmitted through, but only few details can be observed. So some light makes it through, not all of it. It's not as clear. And opaque. Most minerals do not allow for light to pass through, so instead light reflects off its surface. Well, it's the opaque minerals that allow us to be able to say, okay, here's what a mineral's color is. We talk about white light. Roy G. Biv strikes off the surface, the mineral surface itself, and absorbs color. Whatever color reflects off it is the color we see. So the process of seeing a mineral's color is the result of white light composed of Roy G. Biv that strikes the mineral's surface. Some of the energy is absorbed by the atoms in the mineral. We see what gets reflected off the surface. In this scenario here is picture 2. All the colors here, it's a blue mineral. Everything is well, all but blue is absorbed, blue is reflected. One could argue that this white mineral right here would actually reflect all of the colors of this. So we only see what gets reflected to our eyes. Let's go back and look at this picture for a second. When we look at the energy, or we're really considering a small section of visible light spectrum on the electromagnetic spectrum, that the largest wavelength are the lowest frequency, and that's red, and then orange, yellow, green, blue, and violet. In the blue and violet side, these have the highest frequencies and the smallest wavelengths. So we're just confirming the electromagnetic spectrum as to how these colors are just a mix. White light is just a mix of all different frequencies and wavelengths of light. So to finalize a mineral color, atoms absorb and re-emit light. What absorbs and or emits these wavelengths? Well, atomic bonds are generally the culprit. Some elements have electrons that absorb certain wavelengths or colors. These wavelengths provide energy to the elements that will often emit another wavelength to get rid of the extra energy. The energy state of the electron is related to the wavelength that it absorbs. The bonding in this element affects the energy state of these electrons. Therefore, bonds to different elements produce different colors. So elements that produce colors through absorption and emission of wavelengths. However, if there's just a trace of some element, they can still strongly influence the color of the mineral. In other words, small traces of elements can change the color. But there are some colors that are very common as to relating to certain elements in the mineral. Copper, for example, usually produces green and blue colors, and we can see here blue azurite and green malachite. Those are common with copper minerals. Iron is known for red and yellow colors that typically produces. However, almost any element can be responsible for any color. Here's red hematite. Here's a yellow hematite. I'm actually not so sure that that's not even limonite, but they're both just kind of the oxidized iron mineral. Okay, moving on into streak. The streak is the mineral in its powdered form. You could just rub a mineral over the white porcelain plates that we have in class, and you can find that it's streak. And the streak doesn't always have to be the color of the actual mineral itself. Streaking involves rubbing a mineral onto a porcelain streak plate. Often the porcelain plate is harder than the mineral that you're rubbing it onto, so the streak is the mineral that gets pulverized, and we view it in its powdered form. Therefore, a streak is a mineral in its powdered form. Moving on into luster, the luster of a mineral. A mineral's luster is the way light reflects off a mineral surface. Luster can be categorized as metallic or non-metallic. There are several more specific ways to clarify non-metallic. Non-metallic mineral lusters include earthy dull, glassy, or pearly. So if we talk metallic, we can look at galena, we can look at pyrite, and we can look at graphite. These here just have a very specific metallic-y sheen to them. But non-metallic lusters, well, you have to specify it a little further. Here's a dull earthy, here's kaolinite, here's limonite, here's a hematite. The glassy, when we talk about glassy, here's quartz in its crystalline form, kind of a perfect euhedral crystal. Here's massive quartz. Both of these look glassy, as they actually are. That's what quartz is, silicon dioxide. And pearly, we could say talc. Feldspars happen to have this pearliness to them. So when you look at them, it's easy to separate them from metallic to non-metallic, but after you get to the non-metallic, you'll need to make sure you specify what further. So further properties involve hardness. We'll be using Mohs hardness scale, and this is what we'll be using here. So if we take a look here, minerals have different hardness. Soft minerals are easily scratched by a fingernail, while harder minerals can withstand being broken apart by rubbing against other materials. So Mohs hardness scale is this 1 to 10. These are your index minerals. And these include talc is a hardness of 1, gypsum is a 2, calcite is a hardness of 3, fluorite is a 4, apatite is a 5, orthoclase, this is a feldspar at 6, quartz at a 7, topaz at 8, corundum at 9, and 10 is diamond. So we're going to be running different tests. We're going to determine the hardness of minerals. So you need to make sure that you realize Mohs hardness scale is a relative scale, is not an absolute scale. So one of the first things you can do with the mineral to find hardness is just scratch it. If you can scratch it and you're not doing damage to your fingernail, it's softer. If you're scratching it with your fingernail, it's softer than 2.5. And sometimes, unless it's talc or gypsum, you can just say it's less than a hardness or H of less than 2.5. But if it's talc or gypsum, you need to make sure you specify the number using the index number. But if your fingernail cannot scratch it, you can go ahead and move on to a copper penny. And then you'd move on to, we don't really do much with a wire nail, but we have glass. And lastly, we'll use a streak plate. And our streak plates are probably closer to a hardness of 7, but it says 6.5, and that would work. So kind of a heads up here when you're using Mohs hardness scale. In order to find a mineral's hardness, as you're picking it up, just scratch it and observe. If you are uncertain as to being able to scratch it or not, move on to scratching with your fingernail. Right? You don't always have to jump right into one of these. You can just start off, you can go in order. Sometimes you'll get comfortable with them, you can jump right into a hardness test. But make sure you go through the materials that we have in class that are provided. Those will help you get to the hardness. So here we're going to move on into cleavage or fracture. Cleavage is the tendency of a mineral to break along smooth planes parallel to the zones of the weak bonding, whereas fracture is the tendency of a mineral to break without definite shape. So some minerals actually have both. Here we have muscovite. It cleaves very nicely in one direction. Here we have a feldspar that has two very nice planes of cleavage at 90-degree angles. Here we have halite. This actually has three cleavage planes in all three planes, X, Y, and Z. So we have three all at 90 degrees. And here's an example of calcite where we have three cleavage planes that are not at 90 degrees. So when I go back to showing you that some minerals can have both cleavage planes and fracture, for example, the mineral potassium feldspar, K-spar, right here, has two cleavage planes. You can see here's one and here's one here, and these come together at 90-degree angles. But the third plane, the third dimension, is actually a fracture, and you can see it right here. So the picture over here I don't think does a very good job. This is not clear in the picture to the left of feldspar. Therefore, this picture helps illustrate that a little bit more specific. So when talking cleavage directions, we can refer to this page here. This is in our binders. So the number of cleavage directions, it could have one, right? We've got our micas, muscovite, and biotite. You could have two at 90 degrees. There's your feldspars, and here's what it looks like, kind of a schematic. Here's two that are not at 90. For example, hornblende, two planes of cleavage that are not at 90 degrees themselves. We could say three at 90 degrees. You could talk about, once again, here's halite. You could also use pyrite as an example, a perfect euhedral crystal. And you can say three not at 90, and once again back to calcite. So it's these very properties that we just tested, that we'll be testing for, are what lead to gemstones. They're just precious stones. We find them nice. We find them aesthetically appealing. Their hardness, they're durable. Precious stones have been prized since antiquity. The gemstones above, or over here, are cut and polished sapphires from the mineral corundum. And if you recall, corundum is a very, very hard mineral. It's actually number 9 on Mohs hardness scale. So corundum, they're quite durable, but yet they're not quite as hard as diamond, but they come in some really beautiful colors. That trace element impurities lead to color variations. Most gemstones found naturally are overlooked. Gems must be cut and polished before their true beauty is displayed. Gemstones can be considered either precious or semi-precious. A precious gem has beauty, durability, right, it's hard, and rarity. A semi-precious gem has only one or two of these qualities. So if we look at an applied topic to what we're studying right now with minerals, let's consider diamond and graphite. These are called allotropes of carbon. That diamond is very, very strong. It's number 10 on Mohs hardness scale. It's extremely resistant. It's extremely hard. It's pretty much the strongest material naturally occurring, or one of, at least, strongest minerals at least. That diamond and graphite have significantly different properties of one another due to different crystal structures due to forming in different environments, but both are composed of only carbon. So graphite is very, very weak. This is what we use for pencil, what we call pencil lead, but it's what we use. This is graphite, very, very soft. It comes off when we rub on it. But diamond is a hardness of 10. It just happens to be the environments in which they formed that just changes their atomic arrangement, and therefore they have different properties of hardness as a result. And lastly, diamonds. I'm going to give you a little storyline as to how diamonds form and how actually unique they are. Diamonds form deep within the Earth and then are transported by mobile magma to the Earth's surface. So the formation of natural diamonds requires very high temperatures and pressures, and these conditions occur at a limited zone around the Earth's upper mantle. There's a critical temperature and pressure environment that must, let's just say, create the diamond formation where stability is not present globally. It is thought to be beneath the stable interior of continents. So diamonds form in these stability zones and then are brought to the surface by some volcanic activity, and that's where we go and find them.